Hello friend, welcome to the abstract algebra class. It is class 68. In this class we will define permutation group or symmetric group, and also we will define order of the permutation, orbit and cycle of a permutation. First, a symmetric group or permutation group. Let S equal to A1, A2 and so on An. The set of all permutation defined over S forms a group under the operation permutation multiplication. This group is called permutation group or symmetric group. We can say permutation group as symmetric group, both of them same, and is defined by Sn or Pn. Sn or Pn is called permutation group or symmetric group. Here order of Sn is equal to n factorial. That is, order of Sn is equal to n factorial. Order of the permutation. Let S equal to A1, A2 and so on An, and Sn be the symmetric group defined over S, and F belongs to Sn. That is, F such that S into S be a permutation. If m is the least positive integer such that f to the power m is equal to I, where I is the identity permutation in Sn, then m is called order of the permutation F. We know the definition of order and element in group theory. Order of A is equal to m. M is the least positive, which is a to the power m is equal to identity element E. We know it is the definition of order of element in a group, an arbitrary group. Here same as this definition. Here is an order of permutation of group. We get f to the power m is equal to I is identity permutation, then the m is the order of permutation group. Orbits and cycles of a permutation. Here is the definition of orbits and cycles of a permutation. Let the set S equal to A1, A2 and so on An, and F is a permutation defined over S. Now for any fixed element AI belongs to S, there exists as smallest positive integers m belongs to the positive integers such that f to the power m of AI is equal to AI. Here is two cases, orbits and cycles. Then number one, the set AI f1 f to the power 1 of AI, comma f to the power 2 of AI and so on f to the power m minus 1 of AI is called orbits of the element AI. This set is called orbits of the elements AI. The set AI same sets f to the power 1 of AI, f to the power 2 AI and so on f to the power m minus 1 of AI is called the cycle of the permutation F. Here is two concept. One, permutation F is a mapping, a permutation, okay, and also element. Orbits belongs to element and cycle belongs to permutation F. See, let the set S equal to A1, A2 and so on An, and F is a permutation defined over S. Now for any fixed element AI belongs to S, there exists a smallest positive integer m belongs to positive integers such that f to the power m of AI is equal to AI. Then there is two cases. One, the set AI, comma fi f to the power 1 of AI, f to the power 2 f of AI and so on f to the power minus 1 of AI is called the orbits of the element AI. And this is also called the cycle of the permutation F. This is the definition of orbits and cycle of a permutation. Next, we want to prove, we want to solve an example. Here is an example. S is equal to 1, 2, 3, 4, 5, 6, and f be the permutation on S, given by f equal to 1, 2, 2, 1, 3, 3, 4, 5, 5, 6, 6, 4. We want to find the orbit and cycle of element 1. We consider a number 1 AI is equal to 1. Now we f of 1 is equal to f of 1. Image of 1 is 2. F of 2 of 1, f to the power 2 is equal to f of 1 is equal to f of 1 is equal to 2. F of 2 is equal to 1. Actually, here m is equal to 2. Why? Because here if we said already, we said f to the power m is equal to ai. Therefore, m is the order of permutation, or we can say m is the orbit of ai. Here ai is equal to 1. f1 of 1 is equal to 2. f to the power 1 is equal to f of 1 is equal to f of 2 is equal to 1. Therefore, the least positive integers to m is equal to 2. Therefore orbits of the element ai equal to 1 is 2. That is, orbits of 1 is equal to ai comma f1 ai comma and so on f minus 1 ai f to the power m minus 1 of ai is equal to ai comma f1 of ai is equal to a1 ai is equal to 1 f of f to the power 1 of 1, it is equal to 1 comma 2. This it is orbits of element 1 and also cycle of permutation f. Here, if we want to find f to the power 3 of 1, it is equal to f to the power 1, f to the power 2 of 1 is equal to f to the power f square of 1 is equal to 1 is equal to f square of 1 is equal to 1. F of 1 is equal to 2. But it is not equal to ai. Actually, it is not this element which we get 2 is not equal to that element which was, it is not equal to 1. Therefore, 3 is not the order of the permutation of f or the orbits of 1. Therefore 3 is not order of permutation f and orbit of 1. And one, if we choose AI is equal to 4, if we choose element 4, then we want to find the orbit and cycle of permutation f and orbit of 4. We want to solve this. AI is equal to 4. F of 4 is equal to here is 5. F of it is f to the power 1, it is f to the power 2 of 4 is equal to f of 4 is equal to f of instead of f of 4 we can write 5. It is equal to f of 5 we get 6. Now we want to find f to the power 3 of 4 is equal to f of f square f to the power 2 of 4 is equal to f square of 4 we get here 6. It is equal to f of 6 is equal to f of 6 here it is 4. Therefore the actually we get m is equal to 3. Here it is the least positive integers. 3 is the least positive integer, which is we get f of to the power 3 is of 4 is equal to 4. Already we defined f of to the power m minus 1 of ai is equal to ai. Here f of f to the power 3 of 4 is equal to 4, and same definition hold. So therefore we say that the orbit of ai equal to 4 is ai comma f to the power 1 ai comma f to the power 2 ai comma f to the power 3 of ai. It is equal to ai is 4, f1 is 5, f to the power 1 is 5, f to the power 2 of ai is 6, and also f to the power 3 again it is 4. This C is the orbit of the element 4, and the cycle of permutation f is equal to same C 4, 5, 6. It is the solution of this example. Here is another example. Find the orbits and cycle of the permutation f is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 2, 9, 4, 8, 3, 5, 1, 6, 7. We want to solve this, find the orbit and cycle of this permutation for element ai equal to 1. Given that permutation f is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 2, 9, 4, 8, 3, 5, 1, 6, 7. Take AI is equal to 1. We now want to find the orbital cycle of AI is equal to 1. F of 1 is equal to 2. F of f to the power 1, f to the power 2, 1 of 1 is equal to f to the power f of 1 is equal to f of 1 we have 2, f of 2 we have 9. F to the power 3 of 1 is equal to f of to the power 2 of 1 is equal to f to the power 2 of 1, we get 9. F of 9 is equal to 7. F to the power 4 of 1 is equal to f to the power 1 of f to the power 3 of 1 is equal to f to the power 3 of 1, we get 7. F of 7 is equal to f of 7 is 1. Again we reach to 1. Here is also 1, here is also 1. Therefore the orbit of I is equal to 1 is AI f to the power 1 of AI, comma f to the power 2 of AI, comma f to the power 3 AI. Here m is equal to 4. We have 3 minus 1, 4 minus 1. 4 minus 1 is 3. It is equal to f to the power 1, f to the power 1, we have 2, f to the power 2, we have 9, f to the power 3, we get, f to the power 3, we get 7, f to the power 4, we do not have, it is same, repeated. It is the orbit of element AI is equal to 1. Also, it is the cycle of the permutation F. It is the solution of this example for element AI is equal to 1. Now we choose AI is equal to 3. We want to find orbital cycle of for element AI is equal to 3. F of 1, f to the power 1 of 3 is equal to, here from it is 4, f to the power 2 of 3 is equal to f to the power 1 of f of 4 is equal to f of instead f of 3 we get 4, f of 4 is equal to f of 4 is equal to 8. F of f to the power 3 of 3 is equal to f square of 3 is equal to f of f square of 3 we get 8 is equal to f of 8 is equal to 6. F of 4 of 3 is equal to f of f cubic of 3 is equal to f of instead of f of f to the power 3 of 3 we can put 6 is equal to f of 6, we have 5. F of f to the power 5 of 3 is equal to f to the power 1 of f to the power 4 of 3 is equal to f of f of 5 is equal to f of 5. We have 3. Again, we reach to the element 3. Here we have 3. Instead, in this example also, here we choosing A, and also we reach to A. Here we choose 1. Here we choose 3. We reach to the 3. Again, we reach to the 3. Then we write the orbits. Orbits of 3. Orbit of 3 is equal to 3, 1, 2, 3, 4. Here is a to the power m is here, m is equal to 5. M minus 1, 4, up to 4. 3, 4, 8, 6, 5. It is the orbit of 3. Also, it is equal to the cycle of the permutation. It is also is the cycle of permutation. For AI is equal to 3, we get the cycle on orbit here.